Our next talk is from Rajesh Gopakumar, NCTS. He will tell us string theory down to the string theory. Yeah, thank you.
Thank you, Johnson, and it's my great pleasure to be here as part of your celebrations of this 20th anniversary. Thank you very much for inviting me, and all the best for the future. Yes, I have a slightly provocative title about down-to-earth string theory, but I hope you'll see it borne out from what I have to say. So I will begin with something down-to-earth, which is about the liquid vapor and the phase diagram, which all of you have seen from school onwards, of the phase diagram of liquid water and the vapor and the solid. And you know that there is this important critical point in the phase diagram, after which the distinction between the vapor and the liquid phases is no longer clear. This critical point is what is if you wish, the prototypical example of second order phase transition. Why this is very interesting is that it exhibits very novel scaling behavior. Near this phase transition, the correlation length, as many of you know, diverges. Normally the correlators fall off exponentially with a certain length scale, zeta or xi, but near the critical point, this diverges in a very characteristic way, St minus Tc, where Tc is the critical temperature, to an exponent which is called nu, and this is a very this nu is actually very universal, as we will see. It's not just characteristic of water for all liquid vapors, but actually more general. But before I mention that, at the critical point, the correlation function no longer falls off exponentially, but falls off like a power law in the separation. And that power law also has a very characteristic behavior. D is the dimension of so the spatial dimension, in this case 3, for our particular case. But there's a non-trivial exponent eta, and this nu and eta are what are called critical exponents. And these characterize a whole universal class of systems, including what are called binary alloys, various magnetic materials, and so on, which are all captured by a single sort of a simple statistical mechanical model. The universal behavior is captured by the statistical mechanical model, the 3D Ising model. So this is all old stuff, and many of you have probably learned all this in your textbooks. For instance, I just picked out a table from Chaikin and Lubensky's textbook. And you see there are other critical exponents as well. This nu and eta are the ones that I just talked about, coherence length and correlation function. Here it's written in momentum space, but it's the same thing that I wrote down earlier. But there are some others, alpha, beta, gamma, and as many of you know, these were estimated using the Landau-Ginzburg free mean field sort of method, and they give you certain exponents. This mean field gives you certain exponents which are very different from what is observed experimentally, and this is the experimental table. By the way, here there is a n, and the case I just mentioned is the case with n equal to 1. N refers to sort of the symmetry class. More generally, there's an ON symmetry, and the one that I mentioned is the symmetry class n equal to 1, but there are others like n equal to 3, n equal to 2, and so on, and this gives various experimental results. This is probably quite old by now, but anyhow, just to give you an idea that these numbers, for instance, you can see this nu is 0.63, whereas mean field gives you 0.5, and similarly the correlation length is also not 0. The correlation function exponent beta is also not 0. So, and the critical exponents depend on this universality class. Okay, so this is just a review of things that you've probably heard before. And you also probably know that this universality was understood due to Wilson's deep insights into the nature of quantum field theory and specifically the renormalization group. So what does quantum field theory do? Quantum field theory, so at first sight it is surprising that quantum field theory has anything to do with this because I'm talking about a classical system, a classical statistical mechanical system. And whereas quantum field theory describes quantum fluctuations of a continuum system and you apply it to quantum electrodynamics or QCD and so on. But the important idea is that the machinery, the ideas, apply equally well to statistical fluctuations, especially near a phase transition where you can describe by a continuum system. And this is basically due to the mathematical equivalence of the path integral formulation of quantum field theory with a sort of a statistical mechanical system as shown in this picture. So the ideas of Wilson on quantum field theory and the renormalization group, he could transport them to the study of critical phenomena and statistical mechanics. But Wilson's main insight was on that the dependence of the quantum field theory on the scale at which you measure things is captured by an RG flow, a flow in the space of couplings of parameters. There are critical points, such as the one that I just described, are fixed points of this renormalization group flow. So these fixed points are very central to our understanding of quantum field theory, and this is a sort of a pictorial representation of the behavior, let's say near some fixed point like the one that governs the liquid vapor phase transition. Typically, so this fixed point is sort of over here. The arrows draw. This is some slice of the space of all couplings, and these H's refer to the Hamiltonians, the theory, at different scales. And as we change the scale, the Hamiltonians sort of evolve and come to various fixed points. There's a stable fixed point. This is an unstable fixed point. As you can see, this has an unstable direction. And one direction of instability, whereas the others are stable. This one is stable. This is another one, and so on. This just, of course, a schematic. So these fixed point theories are very special, and in fact are central to our modern understanding of quantum field theory because they govern the behavior of quantum field theories. There's a whole regime which is governed by the behavior at this fixed point. And these fixed point theories are special in that they are scale invariant, because as you saw, the correlators have a nice scaling behavior. But what's more, they even seem to be, in many cases, have an additional symmetry called conformal invariance, which is a broader set of angle-preserving transformations. So now scales, of course, when you scale things uniformly, that's one way to preserve angles. But you have more general transformations, so-called special conformal transformations. And this is it's a larger symmetry than what you have, the conventional space-time Lorentz symmetry or rotational symmetry. So these fixed points are very special in that they have much more symmetry. In particular, coming back to the 3D Ising model, which whose critical point describes the liquid vapor phase transition, this universality class is governed by the so-called Wilson-Fisher fixed point, which these two people had discovered. This is a so-called interacting conformal field theory. So CFT is the acronym for a quantum field theory which has this conformal invariance. And it's interacting in the sense that it is not a Gaussian theory, it is not a free field theory. It has a non-trivial interaction. In this case, it's more like a 5 to the 4th interaction of a scalar field in addition to the the usual quadratic scalar field in Hamiltonian. And there is a ON generalization of this involving n scalars transforming as a vector of ON. So these interacting CFTs are believed to govern the fixed points of these ON universality classes that I just mentioned in the beginning. So let me say a little bit about conformal field theories. So how do we, I hope this convinces you that it's very important to understand the dynamics of these very interacting conformal field theories, these so-called non-Gaussian conformal field theories. But we have very few techniques to do that. So it's clearly very important if you want to compute things like these nu and the eta to understand the dynamics, because the mean field answers that I give, which are sort of the Gaussian answers, are not what the actual experiments can tell you. These nu and eta, if you translate them in the language of the quantum field theory, they are captured by so-called anomalous dimensions of operators. In this case, if you compute the 2-point function of the operators in the CFT, they scale in a particular way, and the anomalous dimension at these fixed points is what governs the critical exponents. So there is additional dynamical data in a CFT which is in the 3-point functions. So I talked about the critical exponents refer to the 2-point functions, but there is independent data in the 3-point functions, which for some reason, of course, it probably will change in the future, have not been so much experimentally studied. But this is in principle, conformal invariance constrains actually the form of these 3-point functions severely. In fact, the dependence on x1, x2, x3 is completely fixed by the larger conformal symmetry. This is something very special to the symmetry. Lorentz invariance would not have specified it, nor would, in fact, just having scale invariance specified it. But conformal invariance, as realized by Holography long ago, fixes this up to an overall number, which just depends on the operators 1, 2, and 3. So there's these two. So in a sense, a conformal field theory is specified by just some very simple set of data. The 2-point functions also, I forgot to say, are specified by, space-time dependence is captured by just knowing the anomalous dimensions. So if you know the anomalous dimensions, and if you know these numbers associated with these 3-point functions, in a sense, that's the complete data that you need of the CFT. And it was realized that there are additional dynamical constraints coming from the so-called operator product expansion, which I will come to, which potentially fixes this data. So let me just write it down over here. So sometimes these OP coefficients are denoted by C, I, J, K. If I have 3 operators, I, J, and K. And then there are anomalous dimensions, which are these delta i's. So if it's these data that you want to constrain dynamically to solve for a CFT. Okay, so that's in a sense the setting. And now let me bring in string theory. So string theory, at least from the point of view of its detractors, is often perceived as some kind of a theoretical fantasy in 10 or 26 dimensions, having to do more with quantum gravity, but people think, okay, it's something that you may or may not be able to ever test. But actually, it has turned out to be a fairly broad and versatile framework, very much like quantum field theory itself. And what is quite remarkable is that it gives new insights into quantum field theory and links it in very unexpected ways to general relativity. And the way it does this is very non-trivial. I mean, it is not it's not just empty predictions. It makes fairly non-obvious, very precise, and falsifiable predictions. Falsifiable in the sense that you can actually go and compute from the other side. It makes statements about quantum field theory, front-end relativity, and vice versa. And these are both frameworks that predate string theory. They are the sort of the two main pillars of 20th century theoretical physics. Quantum field theory and general relativity, which have had a long history of independent development, but we have been able to find new statements about both sides through the relationship that string theory gives in connecting these two. So that I see as a very remarkable aspect of string theory, which I think deserves to be appreciated better. And how has this how does this connection work? Well, one very concrete context in which it works is through a proposal of Maldacena, which you might have all heard of, which equates the dynamics of at least a large class of CFTs, these conformal field theories, to gravity of strings in a space-time called anti-de Sitter space-time, which is usually captured in this way to visualize it. It's a hyperbolic space-time, so that's why this Escher drawing of the hyperboloid. And so its cross-sections, you can view them as the spatial cross-sections can be viewed as sort of hyperbolic spaces, Euclidean hyperbolic spaces. And then there is a time direction which is drawn here vertically. So it's sort of an infinite cylinder, which is a solid cylinder with a sort of high constant negative curvature metric. So the holographic relation of Maldacena relates a theory of gravity or string theory more generally in this anti-de Sitter space-time, which exists in any p+1 dimension, to a conformal field theory which lives on the boundary of the space-time, the surface of the cylinder. So it's a d-dimensional boundary, and this is the so-called holographic relation, which of course this prescription comes with a dictionary between observables that you can compute in the bulk, which is this anti-de Sitter d+1 spacetime, and the boundary, the d-dimensional CFT. So there is a precise dictionary between observables on both sides of this dictionary. So this is how you're relating statements about a quantum field theory, in this case a d-dimensional CFT, to statements about general relativity in a d+1 dimensional anti-de Sitter spacetime. But focusing on our particular interest, I told you we are interested in computing this data of a CFT anomalous dimensions. So what do anomalous dimensions, these things that translate to nu and eta, what do they correspond in this dictionary? They correspond to energies in the anti-de Sitter spacetime. So fairly simple, the dimensions are, the spectrum of the dimensions is literally an energy spectrum in the bulk. The 3-point functions are also in the CFT, the ones that I showed you. There are some kind of cubic interactions in the bulk theory. And so this is how one can translate questions in quantum field theory to those in gravity or string theory. And this is what this dictionary helps you to do. And there is a further aspect that when one considers CFTs with a sort of a parameter n, which is measuring the number of degrees of freedom, when that becomes very large, then that's essentially like a classical limit of the dual's gravity theory. So, so you can now go back to the O.N. Wilson-Fisher theory and that I mentioned. And so that's the CFT of interest for phase transitions. And you can try to ask what for large n, whether this has a sort of a classical description in CFT. So this was the Owen-Wilson-Fisher fixed point in 3 dimensions. As I said, we're looking at the 3D Ising model and so on. So its dual would be in one higher dimension, ADS4. So this was actually, the dual was realized more than 15 years ago by these people. And the bulk description is actually unusual. It is a theory of gravity, but not just gravity. It has a single tower of interacting higher spin gauge fields. And this was actually a theory independently written down by the Russian mathematical physicist Vasiliev. It's a very intricate classical theory because there are a whole infinite tower of interacting higher spin gauge fields. And this classical theory is supposed to describe this Wilson-Fisher fixed point. And there are, you can reproduce many known results about the large n theory in a completely novel way with this dictionary. There is a simpler analog of this, which we worked out with Matthias Gaberdiel, which is for 2-dimensional CFTs, for which again there is a 3-dimensional Vasiliev theory. And these describe a class of CFTs which are actually well known. They are the so-called minimal model CFTs. Anyone who has worked with 2-dimensional CFTs might have encountered these. The simplest case with n equal to 2, the SU2 minimal model cosets have the 2D Ising model in them. So just like this has the 3D Ising model, this has the 2D Ising model in this family. And these also have, for n greater than 2, higher spin conserved currents. And this is an exactly solvable example of holography which doesn't require any supersymmetry. So sometimes people say this ADS-CFT is for supersymmetric theories and so on. But everything on this slide is non-supersymmetric. These are pure, well-understood non-supersymmetric QFTs which have the same holographic duality. And this is an example, in fact, where you can, it's a good toy example to study this duality because you can work out things exactly on this side of the duality and to a large extent on the Vasiliev side as well, and make detailed independent checks. It's an example where it could easily have failed, and I won't show you some of the sort of very intricate results that need to match on both sides for this duality to work. So, but let me come back to Wilson. This is not the main point of this talk. Supposing we want to study the 3D Ising model at n equal to 1, which is the n equal to 1 version, if you remember going back to my first slide, then the large n limit is of course not adequate in studying this. Very few people would think that n equal to 1 is large. So you need to do something else. And in fact, Wilson and Fisher themselves had proposed a different expansion, the so-called epsilon expansion, in which you take the dimension of the theory not to be in 3 dimensions directly, but in 4 minus epsilon dimensions. So 4 dimensions turns out to be the case where you don't have this fixed point and you have only the Gaussian theory. But if you go a little bit away in epsilon, then you find a non-Gaussian fixed point, and you can study that in conventional quantum field theory, perturbation theory, which is what Peskin and Schroeder and other books are all about. You can use techniques, perturbative techniques, because the fixed point has a quartic coupling which is proportional to epsilon, and you can pretend that epsilon is small and make a perturbative expansion in this. And through Feynman diagram calculations, you can compute anomalous dimensions to at least to the first few orders in epsilon. And this was done in the famous Wilson-Kogut review. And this are just samples of the expansions for nu and eta, the critical exponents nu and eta that I had on my very first slide. So, so the idea was you compute this now through quadratic methods, and you put n equal to 1 here, and then you hope and pray that it gives something reasonably good. And in fact, it gives you a fairly good description, a fairly accurate description of the fixed point and the critical exponents. So if you just put this in numerically, you'll find even with these results, not bad agreement with the numbers I had on the Chaikin and Lubensky slide. Okay, so this was a technique that, but it has its limitations, as you can see, because putting epsilon equal to 1, you're really, the expansion actually is only an asymptotic expansion, and it's not very clear. You can systematically get better and better answers. So there was a proposal in the 70s for something called the Conformal Bootstrap, which was an alternative to doing Feynman diagram computations to try and determine this data of a CFT. This is supposed to be applicable even when perturbation theory isn't. And it uses the very crucial dynamical ingredient of a CFT, which is that if you consider a 4-point function of a CFT, I talked about 2- and 3-point functions so far, but if I talk about a 4-point function, there are 3 different ways you can decompose it, but let me decompose it in 2 particular ways. One in which I sort of have, I can take an OPE of O1, O2, O3, O4. If I consider a 4-point function, I can take an OPE of these 2 operators, and these 2 operators, I bring them together. That's the left-hand side. 1 and 2 come together, then in the OPE, I get some sum over operators, O, and C1 to O times the operator O and its descendants. And similarly, this one, when I do it, I get a sum over O, C3, 4, O, and the operator, and then I get a 2-point function. So I can decompose it in this way and get a sum over the structure coefficients and the anomalous dimensions of the intermediate operator O, or I can decompose it in an alternate way in which I bring together 1 and 4 and 2 and 3, and then I would get a decomposition now in terms of C23O, C14O. So it's a different decomposition, and this is a quadratic relation between these data and this whole set of data, because it's quadratic in these C's and more complicated dependence on the deltas. So this is potentially an infinite family of equations which you can try to solve, which is definitely supposed to constrain the conformal data, the CFT data. And in fact, it was in solving this in 2 dimensions that one managed to get control over 2-dimensional CFTs, which has played such an important role in so many areas of physics and mathematics. But recently, one of the striking developments was that this program was revisited by these gentlemen here and their collaborators, and a lot of work subsequently. And they implemented this numerically. This is an infinite set of equations, because you have all operators appearing over here. This was implemented numerically, and by truncating, you could get various inequalities that were strict bounds on the conformal dimensions. And this is, in fact, now gives the best numerical values for the critical exponents in 3D. So string theorists are of some use, after all. I think you can see that now, even better than Monte Carlo numerical results are the results for the 3D Ising model coming from here. So I'll just take a couple of minutes. That's okay. So very recently, we proposed a new approach to this bootstrap in which we use inspired by the ADS-CFT duality, we write things in terms of a sum of contributions in anti-de Sitter space in terms of these diagrams are so-called Witten diagrams. They look like Feynman diagrams, but they're actually diagrams in anti-de Sitter space. This ball is supposed to represent that anti-de Sitter space that I drew earlier. And these are operators on the boundary, and there is a well-defined way of computing these diagrams in anti-de Sitter space. You can use this as a basis of expansion, and then what you find is that the conditions, this bootstrap conditions, can be translated into something different in this language, that you find additional spurious powers of positions which you cancel, and that gives you strong conditions. In fact, the best way to do it is an analog of momentum space called the Mellin transform, using the so-called Mellin transform, and in terms of which amplitudes in a CFT have nice meromorphic properties, and now you have to just demand cancellation of various spurious poles. I won't get into the details, but I just want to show you some of the results, because this approach appears to be very effective calculationally. So it's again something that you can see that some of the previously derived answers in the epsilon expansion for nu and eta, we can actually rederive, and we can actually go beyond and compute 3-point functions, which is something that people, even alternatively in the epsilon expansion, people hadn't done. For instance, there is something called the central charge of the 3D Ising model, which is related to the 3-point coupling of the spins of the Ising model with the energy momentum tensor. And this, in the epsilon expansion, it had not been computed. In fact, only the order epsilon square piece had been computed because it's a 3-point function, which is more complicated. So we have a prediction for this, for which there is independent evidence. And in fact, you can see that the numerics for this central charge falls on these dots. This was the previous answer without this epsilon cube term, and with the epsilon cube term, it's much closer. And so you can see that this term, just getting this term gives a big improvement on previous results. And just to show you some other results, the kind of results you can obtain. These are the results for eta, this for the nu and eta essentially. And these are anomalous dimensions for another class of operators which carry spin, including the energy momentum tensor, and higher spin L represents the spin. And you can see that the expressions are quite complicated. And what's new is the fact that you can compute all these 3-point functions. So the terms I've marked in the box are all new terms that people hadn't been able to compute. So you can see the very non-trivial, crazy-looking terms can be reproduced by this sort of method. And we now also reproduce some of the dimensions of pi to the 4th and so on. So just to sum up, and I've just gone a little over time, sorry, so just the framework of string theory is, of course, I think very powerful, and it sheds new unexpected light on quantum fields and gravity through the ADS formulation of CFTs, and it can lead to down-to-earth consequences. So, and I think this connection needs further unraveling, and we need to really understand the underlying mechanism of ADS-CFT. So let me just end with something I just found, a quote from Feynman, which is there from the Feynman lectures, but someone illustrated it, about how Feynman says that a poet once said the whole universe is in a glass of wine. We will never know in what sense he meant that, for poets don't write to be understood. That's typical of Feynman. But it is true that if you look at a glass of wine closely, you will see the entire universe. So I think that's the spirit in which I think one should approach theoretical physics. So on that note, I'll just toast to NCTS for its 3rd decade. So thank you.
Thank you. Any questions?
So this is in some sense you're using holography without using holography. And so my question is that usually when we have this kind of expansion in holography, you're sure that expansion converge.
Yes.
Because you have a holographic tool.
Right.
So in this case, there's no guarantee that you have a convergence.
Yeah, so
expansion.
I expect it to be convergent because I think it is, these Witten diagrams are really like the conformal blocks, but with additional stuff in them, these double trace operators, as you know. So once you impose the cancellation of those spurious terms, then I think what remains are just the conformal blocks of the usual conformal blocks, because the double trace operator contributions are what are supposed to cancel out. So I expect that then it reduces to the usual decomposition of the 4-point function in terms of conformal block. So I think it would be good to investigate that, but the examples that we've studied, at least to these low orders in epsilon, one could actually truncate to a small number of operators, so we didn't really run up against the convergence issue very strongly, but I think it's something one would have to address.
Okay, so the question is actually, just probably, have you encountered other models that are actually not convergent? Because I would expect that at some point you would encounter.
So we are looking at a simple model like 2D CFTs. So the 2D Ising model, you can try to do this, and there I believe that we are at least for some correlators like the energy correlators, you can decompose it in terms of Witten diagrams in a way which is convergent. But I think we need to clean it up and understand it better before I can say for sure.
Also, a quick question about the convergence. You have the convergence. Yeah, you have the expansion in terms of epsilon in one of your results. Maybe.
The convergence
You have the epsilon square and the epsilon cube, but then actually the coefficient are of the same magnitude.
Right. So the epsilon expansion is, we know it is not a convergent expansion. It's only an asymptotic expansion. So because it's like any coupling constant expansion. So that definitely people have studied the asymptotics of that, and you can Borel resum it or and so on. So that's independent of this particular method. So we are using the epsilon expansion as a sort of a test case to reproduce field theory results without doing field theory. Perturbative Feynman diagram results without doing perturbative Feynman diagram calculations. In fact, these come out in just once you set up the full machinery, it just comes out in a few lines. The complicated kind of answers that I wrote down are just a few lines of mathematical code. But anyhow. So that is of course something that we always would encounter anyway. The epsilon expansion is just a test case. One can try to do 1 over n expansion, which would be more convergent. So yeah.
You can also do some on perturbative expansion.
Yeah, so I should have said we have also done a large spin expansion where you can reproduce many of the existing large spin results in the literature. But in fact, there it's actually a convergent expansion, as was recently shown by Karen Quote and so on, and you can actually reproduce those large spin results. That's a more technical question.
Last question.
Yeah. Just make a very simple, naive question. So how about this the gravity part? I think you didn't mention that at all.
Yeah, I was using more the gravity part to learn something about quantum field theory rather than the other way around. I mean, people, in general, I think people have learned less about gravity compared to, I mean, people have learned more about quantum field theory using gravity rather than the other way around. But there are other things where there's a very active set of people trying to explore that in terms of holography. Trying to reconstruct the gravity, trying to reconstruct what the picture of space-time that you have in the quantum gravity regime from the boundary, the issues about locality, issues about the black hole information paradox, and so on. People have been trying to address that using the CFT, yes, but I did it. That's a different set of questions, and it is an active area.
Okay. So, thank you very much. I've been told by the secretary we have to go downstairs to take a group photo. So let's keep Rajesh. Thank you, and then